Hello calculus students, welcome to chapter 3, derivatives. We have actually already done this a little bit in 2.4, so you'll see some similarities there. And in this video, in the first one of section 3.1, we're going to literally define what a derivative is, f prime of x, and then go over some derivative notation. So it's going to look like something we've already done in section 2.4, where we did the limit as h goes to 0. And we're going to do that not just at one point, but for any point on a curve. Let's take a look at the definition of a derivative by first exploring what we already know. We saw in section 2.4 that in order to find the instantaneous rate of change, or like the instantaneous slope at any point A, what we did was we found the limit as h went to 0 of f of a plus h minus f of a all over h. And that's exactly what we did to find, let's say, the slope at like when x was 2, a would just have been 2. And we found what the instantaneous slope or instantaneous rate of change was at that exact point, and we used that to find the equation of the tangent line. But now we want to find the overall definition of the derivative, and that just means instead of finding the derivative or the instantaneous slope at like only one point A, we want to find it for a function at any point x. So instead of finding it just at any point A, I'm going to erase A and just replace it with x. And that's the definition of a derivative. I'll finish it in just a second. And some more notation for us is that this is called f prime of x. So a couple more things we can write is that this is the definition of a derivative right here. And some words I will use before that, just so we don't have this randomly here, is we can say that the derivative of a function f of x is given by this right here. So we say f prime of x, or the derivative of f, is the limit as h goes to 0 of f of x plus h minus f of x all over h. Again, extremely similar, but instead of plugging in a number here when we had it as a just represented any x value like 2, like I said before, we are going to just have x there, and we're going to find the general equation of the derivative, and then that way we can plug in any point into that general derivative of our function. In this first example here, we want to differentiate f of x equals x cubed. Now, differentiate means find f prime of x. So I'm going to write aka find f prime of x, or find the derivative of f. That's just like another verb we can use. All right, so we are going to use that definition that we found before, that we were given before, and we know that f prime of x, the derivative, is defined as the limit as h goes to 0 of f of x plus h minus f of x all over h. And I meant to do this in light blue so we could show the color, but that's fine. I like the navy blue. All right, so we want to plug in x plus h here into this function, and we have not yet cubed something like this yet. Cubing is a little bit more work, but I just thought it'd be fun to do something a little different. All right, so plugging this in, we have the limit as h goes to 0, then f of x plus h is x plus h cubed, minus the regular f of x, which is just x cubed, and that's all over h. Now what I'm going to do off to the side is cube this guy right here. Cubing does have like a shortcut we can use, but we hardly are going to be cubing stuff, so I'm just going to do it off to the side over here. All right, so we'll move a little off to the side, and we're going to cube x plus h, which means we can first square x plus h and then multiply it by another x plus h. And we know how to square something. So to square something, we square the first, then we'll multiply x times h and double it, and then we'll square the h, and we're going to multiply that by x plus h, both in parentheses there. So we're going to end up getting a lot of different terms here. So I'm going to first distribute the x squared through to both of these. So we'll have x cubed plus x squared h. Then we'll distribute the 2xh through to both. So we'll have 2x squared h plus 2xh squared. And then we're going to keep going here. Then we're going to distribute the h squared through to both. So we'll have plus xh squared plus h cubed. Combining like terms, we have 2x squared h and we have a 1x squared h. Then we have 2xh squareds and 1xh squared. So we end up having an x cubed, 3x squared h's, another 3xh squareds, and then an h cubed. So I moved back to the original problem and I replaced x plus h quantity cubed with what we got off to the side. Then I still need to do the minus x cubed here. And of course we're still all over h. Then everything that doesn't have an h in it is going to end up canceling. And so this x cubed minus x cubed will end up canceling. And then we can see that we have h's in every single term. So I'm going to factor out the h in the numerator. In the first term, we're left with a 3x squared. In the second term, we're left with a 3xh. And from the h cubed, we're left with an h squared. And we're still all over h. From this point, the h's can cancel because we still can't put in direct substitution h equals 0, but now we can do the direct substitution for h is 0, and that means that this term will go to 0 because we'll have 3x times 0, and this term will go to 0, 0 squared. So we're left with 3x squared. That means that f prime of x equals 3x squared. That is the general equation of the derivative for our original function f of x equals x cubed. The equation of the derivative is 3x squared. So we can easily find now, f prime of 2. We can find what is the derivative at 2. We have a function we can just use direct substitution in. So it's a little bit different from what we did before. We're not directly only finding the derivative or the instantaneous rate of change at one point. We're finding it at any general point x, any general x, getting an equation for it, and then we can instead use this equation to easily plug in to find the derivative or instantaneous rate of change at any point. So the next thing we're going to do is find f prime of 2. F prime of 2 is very easy to do because we have an equation for f prime of x. It's 3x squared, so we're just going to plug it right in, plug 2 right in. And then we're going to have 3 times 4, which is 12. So we've found that f prime of 2 is 12. That means the derivative when x is 2 is 12. It's a very steep curve at that point because the derivative is such a high positive number. Part C is asking us, is f of x a differentiable function? Now, in order to be a differentiable function, you have to have a derivative exist at all points in your domain. So, does f prime of x exist for all x in the domain of our original function? Well, again, our original function is x cubed. That has a domain of all real numbers. There's no x in a denominator, no x under a square root. And so does f prime of x, this quadratic function, does that exist for all x? Yes, it does. There's no x in here that we could plug in that would give us undefined or anything like that. And so our derivative exists for all of x in our domain, which is all real numbers. So yes, f of x is a differentiable function. It can be differentiated at any x. We could plug in any x into the equation of its derivative and we would get a valid output. In this next example, we're going to do some of the same things that we did in the first example. I threw in g of x here just to show that it doesn't always have to be f, but we're going to do the same thing. So we're going to use the definition of derivative to find g prime of x, the equation of the derivative for g, and g is now a quadratic function, but we're still going to use the same definition. It's a limit as h approaches 0 of g of x plus h minus g of x all over h. Now I like this function. It's a little trickier because we do have to plug in x plus h into two spots. So we'll do that first. We again have the limit as h goes to 0, and then g of x plus h will look like this. We're going to plug in x plus h here, and that one gets squared, plus 3, and then we plug in the x plus h there. So far I've just done this piece right here, g of x plus h. Then I'm going to subtract g of x. G of x is this original function here. Now it's more than one term, meaning that when we subtract, we need to put parentheses around it because we will have to distribute the minus sign all over h. Now this looks kind of crazy, but we'll make it through. All right, we do need to be careful with PEMDAS here. Most of calculus is said, the calculus part's almost over at this point. This is algebra. So your algebra skills need to be, good to go. All right, the x plus h squared is x squared plus 2xh plus h squared. Then I'm going to distribute the 3 through, 3x plus 3h. Then we're going to distribute the minus sign through, so we'll have plus 8x squared minus 3x, and again we're still all over h. It does look like stuff's already canceling, so I'm just going to make this easy on us and see that this plus 3x and this minus 3x will cancel. You don't have to cancel until you're done distributing, but if it makes it easier for you, go ahead. Just be careful. All right, I'm going to distribute the negative 8 through. So we'll have minus 16xh minus 8h squared, and then plus 3h plus 8x squared all over h. So everything without an h should end up canceling out, and it does. We have the negative 8x squared and the positive 8x squared that cancel. In this next step, what I'm going to do is factor out the h because we want the h in our denominator to go away. Since we still can't plug in 0 yet, we can't do direct substitution just yet. So we're left with negative 16x minus 8h plus 3, and of course over h. The h's will now end up canceling, and then we can successfully do direct substitution and plug in 0 for h. That will turn this middle term to a 0 when we plug in, I'll do that in yellow here, when we direct substitute in 0 for h, so it turns this term into a 0. So we're left with negative 16x plus 3. The conclusion that we come to is that the derivative of g, or g prime of x, is the equation negative 16x plus 3. So let's find f prime of negative 1, part B here. We want to actually find what is the derivative when x is negative 1. And I accidentally wrote f. Look at that. I meant g because that's what our function's called. Okay, g prime of negative 1 is, we just want to plug negative 1 into our function, g prime, and that'll give us negative 16 times negative 1 plus 3, so that gives us 16 plus 3, which gives us 19. And the last thing we're going to do is find the equation of the tangent line to g of x at x equals negative 1. Well, remember, in order to write the equation of the line, we need two things. We need the point, and we need the slope. We have one of those things, and we have half of another one. So what we do have is the slope. Remember, the derivative, the instantaneous rate of change, is the slope, and we have the slope at negative 1. It is 19. So we have the slope of the tangent line already. So I'm going to write this in some real cool calculus notation in black here. So the slope of the tangent line is g prime at negative 1. That's kind of cool. It's 19. So we have the slope. We have part of our point. The point is, we know x is negative 1. Now, just to remind you, the original function was this. because it's so far up on the page at this point. That's our original function, OG function. There it is. All right, so we need to find, oh, and again, darn, I wrote F. I mean to write G. It's our OG. All right, so we need to plug in -1 into our function to find what the y value is. So if we plug -1, and I'm going to do that real quick over here off to the side, g of -1, we'll square -1 and get 1, so we have -8. And then it's plus 3 times -1, so it's -3, so it's -11. All right, so our coordinate point is -1, -11. So we have both things. We have the slope and the point. Then we can write the equation of our line. I'll do that in yellow. So we'll have y plus 11 equals the slope 19 times x plus 1. And so we'll have y plus 11 equals 19x plus 19. And then when we subtract 11, we'll have y equals 19x plus 8. And that is the equation of the tangent line, so it touches g of x at exactly 1 point, and it shows that the instantaneous rate of change at that point, -1 and a comma -11, is 19. The last thing that we're looking at in this video is derivative notation. Again, notation is how we note or write things, and in this case, this is how we write or notate derivatives. So these are 4 different ways, one we've already seen, to denote the derivative of the function y equals f of x. One that we'll see sometimes, it's kind of like the lazy way to write a derivative, is just y prime. This little like apostrophe looking thing is always called a prime. This is how we say it in quotes. So this is one way to write it. I'm not going to use this way too often. The other common way to write is dy dx, and it's dy over dx, but the way we say it is dy dx. It is the derivative of y with respect to x. This is the way is probably the most common way I'll write it, and is probably the most common way in calculus to write a derivative. It's f prime of x, or you can just say f prime because x is just so commonly used as our variable. And then another way that we can write it is d dx of f of x. Is kind of a weird one to say. You'll occasionally see this, and instead of seeing f of x here, you'll actually see what the function is. So like if our function was x cubed, you'll have d dx of x cubed. So you can just say it's the derivative of whatever your function is. So again, these are probably the 2 most common that you'll see. Occasionally we'll see this one down here, and occasionally you'll see this one here. The biggest one to know is this one right here, f prime of x. All right, I know that was a lot in one video, but I hope that you understand how to use the definition of a derivative and then how to recognize some derivative notation.